Namaste, bachcho. Welcome to the final revision. I know, exams are just around the corner and the tension is probably building up. But don't you worry at all. Today we're going to walk through every single formula of Class 12 Physics, chapter by chapter, and really understand them. This isn't about memorizing. It's about clearing up your concepts. Let's get you absolutely ready for that exam.
Okay, so here's our game plan for today. We're starting with electrostatics, where charges are just chilling out. Then we'll get them moving in electrodynamics. After that, we'll see the magic of induction and AC, then explore the beautiful world of light and optics, and we'll wrap things up with the mind-blowing ideas of modern physics. Ready? Let's dive right in. So let's begin with part 1, electrostatics. As the name suggests, right? Electro for charge, statics for rest. Here we study charges that are stationary. And let me tell you, this is the foundation for all of electromagnetism, so pay close attention.
And the very first thing we learn is Coulomb's law. The formula is F equals K Q1 Q2 by R squared. Now what this really means is that the force between two tiny point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. That K is just a constant. Its value is 9 into 10 to the power 9. And please remember, this formula is only valid for point charges, and the force always acts along the line that joins them.
Okay, so we understand the force between two charges, but just think about it for a second. What if there's only one charge? Does it have any effect, any influence on the empty space around it? This very question leads us directly to our next big concept. And that influence is what we call the electric field. The formula is E equals KQ by R squared. You can think of it simply as force per unit test charge. Essentially, every charge creates its own area of influence all around it. And Gauss's law? Well, that's like a master key for calculating this field. It says that the total electric flux, the total number of field lines passing through any closed surface, is always equal to the charge enclosed inside that surface, divided by epsilon naught. Whenever you have a symmetrical charge distribution, this law is an absolute lifesaver. Now, so far, both force and field were vector quantities, which means direction was super important. But now we come to a scalar quantity, electric potential. V equals KQ by R. This is simply the work done per unit charge. No direction, just magnitude. It makes the calculations so much easier. And from this concept of potential, we build a device called a capacitor, a device that stores energy in an electric field. The most common formula you'll use is C equals epsilon naught A by D for a parallel plate capacitor.
All right, part 1 is done. We've understood charges at rest. Now let's move forward. What happens when these very charges start to move? Welcome to part 2, electrodynamics.
When charges flow, they create a current, and the king of current electricity is Ohm's law. V equals IR. This is the fundamental relationship between voltage, current, and resistance. So what does the resistance itself depend on? Well, the formula is R equals rho L by A. This means it depends on the property of the material, which is resistivity rho, the length of the wire L, and its thickness or cross-section area A. It's simple, but it's probably the most important formula in circuits. Now here's where it gets really interesting. When a charge moves, it not only experiences an electric field, but also a magnetic field. The main formula for this is the Lorentz force, F equals Q times V cross B. Now everyone please pay attention here. This is a cross product. That means to find the direction of the force, you absolutely have to use the right-hand rule. The force is always perpendicular to both the velocity and the magnetic field. A lot of mistakes happen here in the exam, so please practice this. And this right here, this illustrates the beautiful symmetry in physics. The formulas you studied back in chapter 1 for an electric dipole, for torque and potential energy, are almost identical to the formulas in chapter 5 for a magnetic dipole. Just look, over there it was tau equals P cross E, here it's tau equals M cross B. So don't just memorize physics, try to understand the patterns. It'll make your life so much easier. Let's move on to part 3. So far we've seen that a moving charge creates a magnetic field. But is the reverse possible? Can a changing magnetic field create a current? Well, let's find out in induction and AC waves. And the answer is a huge yes. Faraday's law of induction states that the induced EMF, epsilon, is equal to minus n d phi by dt. In simple words, whenever the magnetic flux linked with a coil changes, that is, the number of magnetic field lines passing through it changes, a voltage gets induced. And that little minus sign, It's not just for decoration. That's Lenz's law. It says that the induced current will always oppose the very change that created it. This is a favorite topic for conceptual questions, trust me.
This induced EMF brings us to alternating current, or AC circuits. In AC circuits, along with a resistor, you also have an inductor, L, and a capacitor, C. The total combined opposition offered by all three is called impedance, Z. And there's a very special condition called resonance, which happens when the inductor's opposition, XL, becomes equal to the capacitor's opposition, XC. At this point, the circuit's impedance is minimum, and the current is maximum. You know your radio tuner? It works on this exact principle to tune into a specific station.
So what happens when electric and magnetic fields start generating each other and travel through space? You get an electromagnetic wave. And when the formula for its speed, c equals 1 over the square root of mu naught epsilon naught, was solved, the value came out to be 3 × 10 to the power 8 meters per second. That was the speed of light. It was this incredible moment when Maxwell proved that light is nothing but an electromagnetic wave. Isn't that just amazing?
So, we've just established that light is an electromagnetic wave. Now that we know what light is, let's study its behavior in our fourth section, the fascinating world of optics.
In ray optics, there are two fundamental formulas you absolutely need to know. The mirror formula is 1 by F equals 1 by V plus 1 by U, and the thin lens formula is 1 by F equals 1 by V minus 1 by U. See that? The only difference is that tiny plus and minus sign. These formulas relate the object distance U and image distance V to the focal length F.
But bachcho, listen to me very carefully. More important than these formulas is the sign convention. I'd say 90% of the mistakes in numericals happen because of wrong signs. Just remember one simple rule. All distances measured in the direction of light are positive, and anything measured opposite to it is negative. Follow this blindly and you will never make a mistake.
Now let's talk about wave optics. The Young's double slit experiment, or YDSE, proved the wave nature of light. The condition for a bright fringe, or constructive interference, is that the path difference, delta x, must be an integer multiple of the wavelength, lambda. And look closely at the pattern on the screen. In interference, all the bright fringes have the same intensity, whereas in diffraction, the central maximum is the brightest, and the intensity of the others falls off very quickly. And now we've arrived at our final section. Here we'll discuss the mind-bending ideas of the 20th century and their practical applications in semiconductor devices. This is where classical physics starts to break down. The first big idea is duality. Through the photoelectric effect, Einstein showed that light can sometimes behave like a particle, called a photon. His equation is K max equals h nu minus phi naught, where the energy of light, h nu, first overcomes the metal's work function, phi naught, and then gives the rest as kinetic energy, K max, to the electron. And then de Broglie proposed the exact opposite, that every moving particle, like an electron, can behave like a wave, with a wavelength of lambda equals h by p. This is the famous wave-particle duality. Using this duality, Bohr gave his model of the atom. His key idea was the quantization of angular momentum, mvr equals nh by 2 pi. This basically means an electron's angular momentum can only take certain fixed values, which in turn fixes its orbits and energy levels. And when we go inside the nucleus, we use Einstein's most famous equation, E equals delta m c squared. This tells us that the mass defect, delta m, gets converted into binding energy, E. And this is the very source of nuclear energy. And finally, we have semiconductors. These materials are the reason all our gadgets, our phones, our laptops, work. From an exam point of view, the relationship between the transistor current gains, alpha and beta, is very important. The formula is beta equals alpha divided by 1 minus alpha. This often comes in direct formula-based numericals, so make sure you remember it. Beta is the common emitter gain, and alpha is the common base gain. And that's it. We started with Coulomb's law and have made it all the way to transistors, covering the entire Class 12 syllabus. You've revisited all the core concepts and the formulas that hold them together. You have completed this entire journey. You should feel really proud of yourself.
So in the end, what's the one thing that connects everything from electrostatics to modern physics? It's our quest to understand the fundamental rules that govern our universe. Now go out there and give it your absolute best in your exams. All the very best, bachcho. Keep practicing and you will definitely succeed.